I had promised a detailed explanation on the converse of Lagrange's theorem. Lagrange's theorem is hailed as the most basic result in finite group theory, and ABCs are finite groups. What is it all about? Let's take a look at it at first. The statement goes this way. Suppose G is a finite group, and if H is a subgroup of G with order n, then n divides the order of G. Let's make it more mathematical with more precise notations. It reads the same. If H is a subgroup of G and n is equal to the order of H, then n divides order of G. This has been rigorously proven to be true. The question we are going to tackle is its converse true? Before we get to that, let's look at an illustration of Lagrange's theorem. Consider the subset of symmetric group of degree 4, interestingly named A4. I'll leave it to you to prove that it is a subgroup. How do we do it? Pause the video, Google for one-step or two-step subgroup test. Use any of your liking. Another trip. It is easy to find the inverse of a permutation in cycle notation. Inverse of cycle 1, 2, 3 is cycle 3, 2, 1, which is equal to 1, 3, 2. Just write the numbers in the reverse order. I forgot we were illustrating Lagrange's. I could count 12 elements in A4. That is, the order of A4 is 12. Can you pause, count, and confirm? We know that S4 contains 4 factorial elements. That is, order of S4 is 24. Further notice that order of the subgroup A4, 12, divides the order of S4, 24. This A4 looks promising. I wonder if it has something more to tell us. Consider A4 and a permutation cycle 1, 3, 4 in it. What is sigma cube? Let's plug 1 in at first. 1 goes to 3, then 3 goes to 4, and finally 4 goes to 1. That's right, we start from the rightmost cycle in this side of the world. Check out 2. Wait, 2 is missing in action. It's fixed again. What about 3? And 3 is also fixed. And finally, 4 is all that's left. And it's fixed too. What does it mean? It means that sigma cube is equal to identity, or that order of sigma is 3. Now that you know how to find the order, can you find all other elements in A4 of order 3? Heard a rumor that 8 of 12 elements are of order 3. If you want, pause the video now and give it a shot. Interesting. Let's see if you remember these basic concepts. For a subgroup H of G, left coset is given by GH is equal to the set GH for every G in G and H in H. That's because G is multiplied to the left or right of H. Does it matter which side? Yes, it does, especially when your group is not abelian. Then there should be a right coset, right? And finally, two cosets are equal if and only if H inverse G is in H. In particular, it is equal to the subgroup H itself if G is in H. You know what the index of a subgroup H in G is and its notation. Also, from Lagrange's theorem, it's easy to observe that index of a subgroup H of a finite group G is order of G by order of H. So far, we noticed some properties of cosets. About A4, the elements of A4 of order 3, and a corollary of Lagrange's theorem that helps us find the index of a subgroup of a finite group G. Before we get to the converse, there's a bigger challenge. What is the converse of Lagrange's theorem? Could this be for a finite group G if order of H does not divide order of G and H is a subset of G, then it is not a subgroup of G? Oh wait, that's a contrapositive, not the converse, and it's true. The real converse is if n divides order of G, then there exists a subgroup H of order n. A very convincing statement it is, isn't it? But is it true? The answer is no, or more precisely, not always. Let's experiment a bit with A4 and its possible subgroups. 3 divides the order of A4. That's pretty evident, isn't it? And our earlier experiment helps us conclude A4 has elements of order 3. And the subgroup generated by that element will also have the same order 3. Hence, the converse seems to be true. Let's try once more. This time, 6 divides the order of A4, 12. Does A4 have a subgroup of order 6? Let's assume that it does. Then, what will be its index? Order of A4 by order of H, that is 2. What does it mean? It means that H has 2 distinct left cosets. So far we showed that H has 2 distinct left cosets. Pick any element in A4 of order 3. There are 8 of them to choose from, remember? Then at least 2 of the left cosets H, AH or A squared H are equal. If AH is equal to A squared H, we can conclude that H is equal to AH or A is in H. In all possible cases, that is, if either H is equal to AH or AH is equal to A squared H or A squared H is equal to H, A is in H. That is, pick any element of order 3 and it is in H. But wait, didn't we say that there are 8 such elements? That's contradicting our assumption that order of H is equal to 6. Bottom line, A4 cannot have subgroup of order 6, even though 6 divides order of A4. And to prove something, you need a rigorous proof. To disprove something, you just need an example. What did we just disprove? The converse of Lagrange's theorem is not true in general. We proved Lagrange's theorem and illustrated it with an example. Proved that its converse is false with a counterexample. But do remember, I told you, is the converse of Lagrange's theorem true? The answer is not no, but rather not always. That's because partial converses are true. We already saw it with 3 dividing order of A4. Some keywords that will help you in that pursuit is shown here, like converse is true for finite abelian groups. Do try googling about them. That's it for now. See you soon.